Hello, so today we are going to do this problem which is part of Leetcode daily challenge. Find eventual safe states. So basically we have a graph of n nodes and these nodes are from 0 to n minus 1. So for example here we have 7 nodes from 0 to 6. And then we have this concept of a terminal node where basically it's a node where you have no outgoing edges. So for example 6 here is a terminal node because there is no edge coming out of 6 to another node. Also 5 is a terminal node because there is no outgoing edge. The only edges are from 2 to 5 and then from 4 to 5. But those are incoming, okay? And we have this concept of a safe node where basically it's a node that where every possible path starting from that node leads to a terminal node. So for example here if we take 2, all the paths from 2 lead to a terminal node. So one path from 2 leads to 5, which is terminal node. Another path from, that's the only actual path from 2. All the other ones are incoming edges, right? And so we can say that 2 is a safe node. So that's the idea, and the goal of the problem is to return an array that contains all the safe nodes of the graph, and we want them in sorted order. So in this example again, we already determined that 2 is a safe node. 4 is also a safe node because the only path from 4 is to 5, and 5 is a terminal node. And so 5 here, and 5 itself is a safe node because there is no path from it out to anything, and so it's a safe node. Similarly for 6. Okay, so that's the idea here. Now let's see how we can tackle it. Okay, so how do we handle this? So the way to think about this is, let's say first, when can we mark a node as not safe? Well, the answer is if we find a path that doesn't lead to a terminal node, then we can mark a node as not safe. But not only that, we can mark the node as not safe, but we can also mark all the nodes in that path as not safe because they led to a non-terminal node. And so let's see an example here of that. What's a path that sorry. So for example, if we take this 0 here, it goes to 2, okay? But then 2 goes to 5, so that's a terminal node, so that's not the right path. But what if we take, let's say 0 to a 1, right? So 0 to 1, okay? And then we go from 1 to 3, okay? 3 goes back to 1. So this is already, 0 is non-terminal node, 3 is non-terminal node. So this path led to a non-terminal node, right? And so that means definitely 0, which we started from, is a non-safe node. But also that means that 1 is a non-safe node, right? Because we just found a path that leads to a non-terminal node. So 1 is not safe, 3 is also not safe because 3 also goes to 0 and then you go to 1 and then you go to 3, so it's not a safe node as well. So that means we can mark all 3 as non-safe. And from that moment on, every time we do a walk through any other nodes and it leads to one of these 3 nodes, right, we can stop right there and say that that node is not safe as well. We don't need to do another DFS traversal. And so that's the approach we are going to take here. And basically, if we do a traversal from one node and we don't find any unsafe nodes, right, we only get to a terminal node, we can mark the node as safe. And then as well next time, so for example, we mark 5 as safe. That way next time, if we ever reach 5, so let's say we go from 2 to 5, we find that this is safe, right? So let's do actually something like this is safe. Then we mark 2 as safe, right? We mark 2 as safe only if we don't find any neighbor from 2 that is safe, that is unsafe, and that's the case. Similarly for 4. So that's sort of the idea. Once we mark all the nodes as safe or not safe, we can use a map to mark them because we want, if a node has not been marked as safe or not safe yet, we want to be able to identify that. And the way to identify it is if it's not present in the safe map, right? So that's the core idea here. And then at the end, we can just go through this map, and then all the nodes that are set to safe, so maybe we can set the value to true if it's safe and false if it's not, then we can return those. So with just a simple DFS, we can do this. Just a DFS on this safe map here, and then we can accelerate the time here by marking all the nodes that are in a path that lead to a non-terminal nodes. We can mark all of them as unsafe, and that way we can accelerate it, because here the time, this takes, we have up to 10 to the power of 4 and 4 nodes, and so with this DFS is going to be at most 10 to the power of 4, right? So that's the idea. Now let's just code it up. So we said we need a safe map, right? So let's actually have define that. So just a safe map like this. And then we need to go through a nodes. So first, the nodes are 0 to n minus 1. So let's call this actually a node. And what is n? N is just the length of this graph list. So n is going to be the length of the graph. And here we will say check. We'll just do a DFS. Let's call it is safe or check safe. It's going to be DFS function. And we want to define this function somewhere here. Okay. Let's call it that. And then once we apply it to all the nodes, right? We want to go through all the nodes. So let's call this safe nodes. That's what we want to return. And then we will go through all the nodes and check if they are safe. So if they are safe, so because this will traverse all the nodes, we are guaranteed that it will do that. Then we are guaranteed that all the nodes will be marked in this map. And so we are guaranteed that this key always exists. And so we will just append to this list of nodes. Okay. And then we check safe here. And so what we will do is we will say if node is in this safe map, then we don't need to check anymore. We already determined whether it's safe or not. So we already cached it, so we just return it. However, if not, we just want to go through all the neighbors. But we also want to mark it first initially as not safe until we determine that it's safe. So we assume it's not safe first until we determine it's safe. So how do we determine it's safe or not? Well, we just go through all the neighbors and see if any of the neighbors is not safe. That means the node itself is not safe. But if any of the neighbors is safe, like a terminal node, for example, then we will mark all of them as safe, right? And so here, if not check safe, so this returns basically whether node is safe. Okay. So if any neighbor is not safe, then here we want to return false. But we also want, we already set this to false, so we don't need to set it again to false. But if all the neighbors, so at this point all neighbors, okay, led to a terminal node, right? Because all neighbors are safe. Okay, led to a terminal node. So that means the node is safe, because that's the literally the definition is, so we need to mark the node as safe. Okay, then here we return true, so that all the other nodes in the path will get this as true, and if they don't have any other neighbor that is not safe, then they will be set to safe, right? So that's the idea here. And now this should be good, so we can just the other thing is the result needs to be in ascending order, but because we are going through the nodes in sorted order, then this would be sorted. So that's the idea. Now if we run this and submit, it does pass. Okay, so that's the solution here. Now in terms of time complexity, we are using a DFS here. So every time we traverse a node, we will mark whether it's safe or not. So we will go through the nodes only once, and so it's going to be O of n, the number of nodes, and then this is the number of nodes. This goes through the number of nodes. So overall, it's O of n time. And then in terms of space, we are using this safe map and this list of safe nodes, so it's also O of n space. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you in the next one. Bye.